to the limit one more time. Take it to the limit. Take it to the limit.
Well, you've guessed it. We're going to take it to the limit one more time. And we're going to start with limits analytically. So let's first jot down, our first goal is going to be to try direct substitution. If that doesn't work, we can factor or even use the conjugate method. And we'll make another note here. We can also apply L'Hopital's rule, or L'Hopital, if and only if you get 0 divided by 0. Now this has a special name, of course, and that is indeterminate. So let's go ahead and try a few examples. Number 1, the limit as x approaches 5. Well, remember, your first goal is to always try direct substitution. So I'm going to plug in 5, and I'm going to get 5 squared minus 24. So 25 minus 24 is 1, divided by 5 minus 5, which is 0. Now take special note, this is not L'Hopital's rule. We do not have 0 over 0. Just ask yourself, what is 1 divided by 0? Well, of course, that's undefined, so I would say the limit does not exist. Question 2. The limit as x approaches 11 of the square root of x plus 5 minus 4 all over x minus 11. Now, if I try to plug in 11, direct substitution, which I should do first, I'm going to get 0 over 0. So I could use L'Hopital's rule right off the bat, but I want to review another method known as the conjugate method. So we just multiply by the conjugate of the numerator. So I'm going to say I have radical x plus 5 plus 4 and radical x plus 5 plus 4. Okay, now, you do obviously have to do some foiling, so I'm going to keep the limit as x approaches 11, and I'm going to multiply this, which is simple because any radical times itself is just x plus 5, or itself. And a conjugate's nice because the middle terms will always cancel, so if you have to show it, but hopefully you know that by now. And my last, I'm going to get a minus 16. Now, the one thing we never want you to do in the denominator is actually multiply. Just write these quantities down. X minus 11 times the quantity radical x plus 5 plus 4. Now, of course, there's a reason for that, and you'll see it in a moment as we clean up. In my numerator, I get x minus 11, and you'll notice how nice that is because I'll have an x minus 11 on the bottom. So that's why we didn't want you to waste your time cleaning that up. Then my x minus 11s can cancel, so I get 1 over this quantity. And now don't forget to actually take the limit. Go back and substitute 11 in. And I get 1 over, what is that, 4 plus 4, so 1 over 8. Whoops, I'm squeezing it in there, 1 over 8. Now, like I said, I had 0 over 0, so we could use L'Hopital's rule on this. So let's go through and do the same problem with L'Hopital's rule. Basically, all that rule says is you're going to derive the numerator and derive the denominator. We are not using quotient rule. So if I derive the numerator, I'm going to get 1/2 x plus 5 to the negative 1/2 times the derivative of the inside, which so times 1. The derivative of 4 is 0, all over 1. And I'm just going to clean that up and say that's really 1 over 2 square root of x plus 5. I'm going to carefully plug in my 11. I get 1 over 2 times 4, so I get 1 over 8 this way as well. So either method, again, as long as you have 0 over 0, you can use L'Hopital's. All right, example 3. Again, I'm going to try direct substitution. I don't see any type of factoring or conjugate method. So if I plug negative 1 in, I get negative 1 plus 1, which is 0, divided by 0. So again, and you're going to find this a lot, we see L'Hopital popping up over and over on our AP. So let's go ahead and apply it. We're going to keep that limit and take the derivative of the numerator and the denominator. So I get 3x squared over 1. And I'm going to plug in my limit again. And hopefully we get 3. Now I do want to make one more note about L'Hopital's rule. Let's say you plug in right away in your direct substitution you get 0 over 0. And then you take your derivative and you get 0 over 0 again. Well, you know what? You just keep applying L'Hopital's rule over and over until you get an answer. Maybe you have to take the derivative again and you get 0 over 0. And then maybe on the next time around you actually get an answer. Okay, so again, you can use L'Hopital over and over and over until you get an answer. All right, let me give you another example. This one looks a little uglier. The limit as h approaches 0, tangent pi over 4 plus h minus tangent of pi over 4 over h. So again, I always am trying direct substitution. So if I plug that 0 into h, I'm going to get the tangent of pi over 4 minus the tangent of pi over 4 over 0, so 0 over 0. So again, I'm going to use L'Hopital's rule. Okay, we keep that limit as h approaches 0, and just talk yourself through it. Derivative of the numerator over derivative of the denominator. Now, the one thing I ask myself is who's the variable, and it's whoever the limit is about. So I'm treating the h's as the variable in this function. So I've got an outside, inside, so I'm going to say it's secant, what's happening to my pen? Secant squared of pi over 4 plus h times the derivative of the inside. Well, pi over 4 is nothing, and h is times 1. Minus the tangent of pi over 4. Now be careful, do you see a variable there? Okay, no, that is a constant, so its derivative is 0, all over h, which is 1. So as I clean this up, I'm going to get the limit as h approaches 0. We want to carry that limit through. Secant squared of pi over 4 plus h, all over 1, and I get secant squared of pi over 4. Now, of course, we want to evaluate that. So I'm going to say to myself, okay, secant's the reciprocal of cosine. The cosine of 45 is radical 2 over 2, so I'm going to flip it upside down. 2 over radical 2, and I need to square it. So I get 4 over 2, or a final answer of just 2. All right, so we're going to make it even more interesting now. And here, I just grabbed this one off one of our previous AP exams. Okay, so now, take note in this one. Do you see two variables? Okay, you see an x and an h. Now here's the deal. You're not going to have two variables. Go back and read the limit. This is who you're treating as the variable. Everybody else is a constant. Okay, so maybe you need to star that in your notebook. Let me repeat that. The limit we're approaching is h, so that is the variable. Everybody else will be treated as a constant. Okay, so if I plug 0 into h, I get the ln of 2x minus the ln of 2x. I get my 0 over 0. So I'm going to go ahead and use L'Hopital's rule. So the limit as h approaches 0. Okay, now keep saying to yourself, this is the variable, everybody else is a constant. To take the derivative of an ln, I'm saying du over u, so the derivative of 2x plus h. Be careful. 2x is a constant. So I'm going to get 1 over 2x plus h. Minus x is a constant. Its derivative is 0, all over 1. So as I plug in now my limit as h approaches 0, I'm going to replace the h with 0, and I'm going to say my final answer is 1 over 2x. Okay, so one little hint is anytime there's an x in the problem, you're going to have an x in your answer. You're not going to get a finite constant or number as your answer. All right, so let's try another similar one. But remember, whatever the limit approaches is the variable. Any other thing that looks like a variable is actually a constant. So here we have it. The limit as h approaches 0. So again, I'm going to substitute it in. 0 over 0. All right. So again, I see x's and h's, which means if I see those x's, I know I'm going to have an x in my answer. But I'm going to go back here and say the variable is h. Treat every other letter like I see as a constant. So the limit as h approaches 0, I'm going to take the bottom first, that's just a 1. Okay, nice little chain rule, 3 times the quantity x plus h squared, now times the derivative of the inside. X plus h is just times 1. This bear right here, don't get fooled, it's not 3x squared. The variable is h, therefore the derivative of anybody else is a constant. Okay, take that limit, plug it in, so I'm going to get 3x squared as my final answer. All right, our next little topic will be limits as x approaches infinity. All right, and hopefully in your head you're saying power fight. And basically here's the deal. If it's a fraction, and it doesn't have to be, so let me stress that, but if it's a fraction, you're going to compare the largest power on top in the numerator to the largest power in the denominator. And there's 3 different outcomes that can happen. So first, if you get small over large, that answer is always going to be 0. If you get same over same, we're going to go with the ratio of the coefficients. And lastly, if you get a large over small, we can say two different things. Some textbooks like to say does not exist, but our AP mostly uses plus or minus infinity. And you'll have to figure out whether it is a positive infinity or a negative infinity. And let's go ahead and start this in our notebook. You always want to plug infinity in to determine the sign, again, whether it's positive or negative. All right, I got a couple for us to try together here. Now, like I said, we're only doing a power fight if there's actually like a fight. If there's a fraction, you can still take a limit if there's not a fraction. You're just going to still look for the largest term. So basically what I'm trying to say is I'm going to quickly scan for the largest term, and it's this x to the 4th term. So these don't mean anything. Okay, so I'm just going to plug infinity in. If I have negative 10 times infinity to the 4th power, okay, clearly this is going to get me a huge number, but when I multiply it by 10, or negative 10, it's now going to get me a very negative huge number. So I'm going to say that answer is negative infinity. Let's take a look at another one. The limit as x approaches infinity. So again, I'm thinking power fight. So I'm just going to search the top row for the largest power, and basically I'm going to box it in for myself. These mean nothing. And I'm going to search the bottom for the largest power, box that in. Those mean nothing. And now I'll look at my powers and see who's larger. Well, x squared is smaller than x cubed, so I would say that's a small over a large, so my final answer is 0. Now, it gets a little more interesting with trig functions. The limit as x approaches infinity of sine theta over theta. So again, I'm going to substitute it in because I don't really have powers to compare, so I'm just going to substitute infinity in and ask who's bigger. Well, I already know the denominator is very large because it's infinity itself. So now I'm going to think about the sine graph. As the sine curve goes out forever and ever and ever to infinity, notice it's always going to wobble between heights of -1 and heights of 1. So if I compare heights of -1 to 1 to a number of infinity, who's larger? I would say that's small over large, so again I'm getting 0. Next one, the limit as x approaches infinity. So it's a fraction, so I'm going to think power fight, but again, I'm going to substitute it in for myself. Who's larger, e to the infinity or infinity to the 5th? Well, remember, the definition of exponential is an extremely fast-growing function. So I'm going to say I have a large over a smaller number. So now I just have to determine if it's positive or negative. So remember, this is going to either get me plus or minus infinity, and now just ask yourself, e to the infinity is positive, and infinity to the 5th is positive. Therefore, I'm going to get positive infinity. Next one, the limit as x approaches negative infinity. All right, so I'm going to start with my power fight again, because I have a fraction. And I'm going to say I have large over small. So I know my answer is either positive or negative infinity. So I'm going to narrow out all my other choices. Now I've got to use some good logic here. I'm going to plug negative infinity in. So if I substitute it in the numerator, negative infinity to the 4th is a positive number. If I substitute it into the denominator, negative infinity cubed is negative times 2 is a negative. So that's going to imply that this answer is actually negative infinity. And our last power fight, again I have a fraction, so I'm going to do an infinite limit. So I'm going to ignore this number, and I'm going to say I have large over small. So I know it's plus or minus infinity. Now I'll determine which one just by substituting it in. I'm cubing infinity and then making it negative, so that's a negative. And here I'm squaring infinity, which is a positive, so again I'm going to say my answer is negative infinity. Alright, so now we're going to take a quick look at limits graphically. So you'll notice we have the definition of a limit down. You should be pretty familiar with by now, but let's get it in there anyway. The limit as x approaches a from the left of f of x has to equal the limit as x approaches a from the right of f of x. So basically, as I go this way and this way, I have to meet each other. And the easiest way to think of this is a function's intended height. Okay? So let's go ahead and take a look at this picture. And let's start with the limit as x approaches -4 of f of x. So here's what I'm doing. I'm basically taking my pen and I'm moving it along. I'm saying, as I approach -4 from the left and I approach -4 from the right, do I intend to get to the same height? Absolutely. I intend to get to a height of 2. Now, does it matter if I actually get there? Heck no. All I care about is my intentions. I intend to get from the left and the right side to a height of 2. Let's try the same idea with the limit as x approaches 1. Oops. So, I'm going to ignore that line I just drew. I'm going to come in from the left side, and I'm going to get closer and closer and closer to 1 from the left. There I go. And I'm going to come in closer and closer and closer on 1 from the right. Did I intend to get to the same height? Well, not even close. They're not even near each other. So now I can say the limit does not exist. Let's try the same thing just and talk it out through the limit as x approaches 6. When I come in from the, oh dear. When I come in from the left, oh my goodness. When I come in from the left, I intend to reach a height of 5. And when, oh my word. Well, I can't move my arrow. I'm just going to move my cursor here. When I come in from the right, I intend to reach a height of 5. Since they both intended to get to 5, whether or not they do or don't doesn't matter. Their intentions were there. The limit is 5. Well, I've got one last one for us to play with tonight, and this has appeared on our past 2 AP exams, so we can kind of suspect we're going to see it again. The limit as x approaches 3 of the absolute value of x minus 3 over x minus 3. And I think the easiest way to attack this is just to solve it graphically. So the first thing I'm going to do is just plug some numbers in. For example, I'm going to plug in a 1. So on top I'd get 2, because it's the absolute value, all over -2. So when I plug in a 1, I get a height of -1. And I'm going to plug a 2 in. If I plug a 2 in, I get the absolute value of -1, so I get 1 over -1. Now what happens when you plug a 3 in? I basically get 0 over 0, so I know it doesn't exist at 0. So what I'm going to do there is I'm going to put a nice big hole because that function doesn't exist. And basically, I could plug more points into the negative direction, and I'm going to get heights of -1. So what this function is doing is it's getting closer and closer to 3, but it's not actually touching it. Now remember, there's numbers that exist between here, 2 and 3. So you could plug in 2.99999, 2.99999, and you're still going to get -1. So that's why we want to make sure this function goes right up till 3 where there's a hole. Now let's go ahead and plug in +4. If I plug in 4, I get a +1. If I plug in 5, I get a +1. 6, I get a +1. But again, if I get close to that 3, I'm going to get a nice big hole. Okay, so we call this a nice little step function. You can kind of think of it as taking a step up to one another. So as you look at it, what is the limit as x approaches 3? Well, when I come in from the left, my intended height is -1. But when I come in from the right, my intended height is +1. So I would say the limit as x approaches 3 does not exist. But this is something we want to make sure we can, sketch out for ourselves. Well, that does it for our limit review. Have a great night.